So over to Professor Gokhale.
Very good morning. Thank you, audience, and thank you, everyone. This is Gokhale Jayanti, and I'm signing in from Mumbai. And it's a pleasure to be part of this Tech Fest 2024, coming out from Open Tech Foundation. Today, I'm going to be talking on a very, very elementary topic, and I'm given the simplest of all the topics that are there in the day. And my topic would be centered around a simple understanding of what we mean by machine learning models. So, let me, with your permission, share my screen, and then I will also bring up a presentation. Uh, I hope my presentation is visible. So let me get this started with the proceedings of the day. So I'm going to talk about learning models and base algorithms, which are popularly used in machine learning applications. And my focus is not really into talking about some very complex algorithms, but I'm going to do a, let's say, a session from the grassroots levels. So it is targeted for newbies, right? So that is what I'm going to typically focus. Kindly give me 1 hour to 1 hour 10 minutes, and then I'm going to give a complete overview of what goes into various ML models. Okay, this is a brief profile of mine. I have about 40 years of both academic as well as industry experience, and I have a passion for talking, teaching, and I also currently work in this area of machine learning uh, and allied fields as well. So, a quick agenda. I'm going to talk about what is meant by the ML framework. We will quickly have a discussion about what are the various methods that are adopted for machine learning. We call them as the learning methods. And there are various machine learning models. So we'll also talk about what is meant by a model, and we will quickly illustrate a few of these particular models. I'm not going to show you complex math out over here, but I'm going to just set the context out over here so that you appreciate what are the various models and where you can possibly use these models. If time permits, I'm also going to talk about some underlying algorithms into a few of these models. And as I discuss about each of the model, I will also list out what exactly are the basic applications where a specific model can be used. And at the end, I will keep the stage open for any questions, and I should be happy to answer your questions as well. So let's get started. And what I'm going to do is I'm just bringing up some things on a very, very lighter note. So on a lighter note, here is what we talk about. You know, Alexa happens to be a part and parcel of your daily life. Most of the homes have Alexa, and Alexa is supposed to be a quote unquote a voice assistant, right? You can just issue a command, and it typically executes the command, interacts with us over a voice type of an interaction. So this is a case where Alexa is being used for an extended type of an application, I should say. Here is another small example. Here is a interaction between an interviewer and the so-called person, and that particular so-called person is supposed to be a part and parcel of a learning system. ECA, the machine learning system. And here it's an interaction where the interviewer typically asks me what exactly is 9 plus 10. I give out an answer 3, which is incorrect, and the interviewer tells me it is 19 as the correct answer, which I once again understand his answer and I try to respond back as 16. Interviewer once again corrects me and then tells me it is 19, and then I come back and then say, oh yeah, it is not 19, maybe it is 18, and the interviewer enforces that it is 19, which I agree. And this shows the fact that I'm showing a very nice propensity to learn, to correct myself, and that is the reason why I get hired even by the company. Just to indicate the fact that machine learning algorithms go into this entire process of learning, right? Learning from your mistakes, right? Another small example, this is typically what we might be seeing in the future. If you go to a restaurant, you probably might not be having any choice as to what you need to order. The things are pre-decided, and whatever is decided by AI or maybe a complex machine learning algorithm, that would be typically served for you. Right? So these are some very simple illustrations just to bring out the fun aspect of today's session. But let us take a small example which is a little more serious. So a serious example is something like this. Imagine there is a company, and this particular company sells ice cream. And the owner of the company, a young guy, becomes a little curious. He says that, okay, why don't I keep a track of what is exactly happening and to the sales of my ice creams based out on the day-to-day recorded temperature. So he maintains a small diary, and then records for about 20-21 days of observations. He records what exactly is the temperature on that specific day, and also records the sale amount. Right. So once his data is there, he would like to see if at all this particular data could be of any significance. Right. Immediately he can draw some basic inferences, and from the basic inferences he can deduce the fact that the maximum sale is about 7,500 maybe dollars. Minimum sale is about $3,600, and an average sale hovers around $6,000. So this is something which he can get infer directly by looking at the data that is recorded, and then he can apply a few statistical operations, right? Minimum, maximum, average. These are the statistical operations I can perform on the data, and from here I can possibly get some rough estimate. So what is the estimate I can get? Oh yeah, so today possibly I can expect a sale of somewhere around 6,000. And definitely I don't have to overstock myself. I don't have to really bring in stock more than about 8,000. Stuff like that. These sort of indications will help him fine tune his business. Right. So the data which he has got is now going to effectively use to make some inferences which are, let's say, well informed judgmental decisions which he is taking. Now, not only that, is this possible that with this data, can he predict the sale once he gets some indication about the temperature? So let's say the next day he opens, and then he gets a weather forecast saying the fact that on this particular day the temperature would be hovering around 29 degrees. So from there, can he typically get some estimate as to what is the type of a sales he can anticipate on that particular day? And to answer this, he has to really identify if there is some sort of a correlation between the temperature and the sales. I think it is pretty very obvious. As the temperature increases, demand for ice cream also increases. And if the temperature falls down, the demand for ice cream and the sales for ice cream also falls down. So we can say that there is a direct correlation between these two parameters, right? The temperature and the sale. Having said that, is it possible for me to have a more realistic estimate? Can I exactly predict pretty close to this sort of observed behavior based on the observed facts which I have got? Is it possible for me to exactly predict what would be the sales given a temperature of a particular day? So what we do is something like this. I need to build a mathematical representation of this entire scenario, and that is what we call as a mathematical model. Just imagine using some magic, I can come up with this sort of a functional relationship when I say the sale is a function of temperature. I think it is pretty very obvious. And I now need to define what exactly is that specific function which operates on the temperature values so as to translate this into a specific value for sale. Right? So how do I do that? First and foremost, I will come up with this sort of a functional model. That's a mathematical model. And then I will typically use the observations which I already have, about 21 observations which I already have, and use these observations to actually set up the model for me. And then before I really apply the model, I will test whether the model is working fine or not. So I just test out the goodness of the model, whether the model is good to use, whether the model is going to give me accurate results, and so on and so forth. So I'll test it out. And once I can test it out, I get confidence in using the model. And I say that, yes, my business so far for the last 21 days is as per this mathematical functional representation. So I can say that. So once I have gained that sort of a confidence, I can now use this particular model to actually answer my question. If today's temperature happens to be 29 degrees, what will my model predict my sales would be? Right? My model would predict probably the sales would be around $7,200. Very much possible. Very much possible that instead of $7,200, the predicted value, I might actually make a sale of $7,100 or probably $7,400. So just also means the fact that if there is a slight deviation of the actual value from the predicted value, we say that, okay, my model can now be refitted. I can fine tune the model so that this sort of anomaly, this sort of an error in the prediction can be reduced. Just remember these aspects. So we build what is called as a regression model, and this is what is also called as a linear regression model. And what I typically do is something like this. I identify a linear relationship between the temperature and the sales. So along the x-axis, you have got the temperature. We call this as a dependent variable. And using this dependent variable, sorry, this is an independent variable. Using this independent variable values, we determine what exactly is the value of the sale, the so-called dependent variable. So I define this sort of a linear functional relationship. It's a line sort of a relationship, a linear relationship between these two parameters. And if I know the fact that the temperature is 25, the predicted sale would be, let's say, 5250. If the temperature is, let's say, 29, I project it onto this line. Probably I'll get about 6,800 as my sale amount. So this is how typically I can do my prediction. So this is a wonderful mechanism wherein I have used the data. From the data over the past, let's say, 21 days, I have prepared a model. Maybe if at all I have got, let's say, data over the last 40 days, I would have definitely prepared probably a better model. 60 days, even so better model. So which also means the fact that if I have more data available with me, my model can be that much more effective. It can be that much more powerful. It can be that much more robust. It can be that much more accurate. Right? So this entire concept is all about building models, and machine learning is all about developing models. Artificial intelligence, which also uses machine learning, is all about developing models, right? So how do I typically develop models? Right, first and foremost thing is you have to have a crisp understanding about the underlying behavior. So what is the scenario? What is the scenario you're trying to address to? You need to have a quick understanding of the underlying behavior. Then, having understood that, you now try to work out with a bunch of math. This particular math could come from probability, could come from statistic, could come from your understanding of how to handle random variables and stochastic processes, linear algebra. You just name it. You can just make a small bhel puri out of all these math techniques and create the so-called models. And once you have the model ready, you can now set up a small program which implements this particular model. And for this, you can use Python or R or Java, C++, or whatever might be the programming language. You use a specific programming language which you feel is good enough supporting the so-called underlying APIs or the libraries. So build up the program and then ultimately serve this program or deploy the program so that people can start using this prediction model. Okay, so this is all about modeling. So let us now quickly understand what is this concept of machine learning. Today's session is all about machine learning models. So let me first get started with a quick understanding of what goes into machine learning. Simply put, machine learning is all about identifying a bunch of algorithms that learn from the data in the context of an underlying system, and all this happens automatically. In a conventional mechanism, what you do, you understand a problem, you understand what the problem is all about, and then try to implement this as a bunch of functions. So you do what is called as a functional programming. You implement the set of functions to generate the solution to a problem, and once that functions are clearly identified, you apply these functions to process the data and generate the results. Whereas in machine learning, it actually goes the other way around. Okay, you have an access to the data and you identify, okay, this is the outcome I need to have. So then you typically start working backwards to create the so-called algorithm. That is what is called as a model. Okay, so how do you do that? You create some sort of an algorithm, find out if that actually is working well. If not, make a small edit to that algorithm, and then once again try it out. So there is a iterative approach that is set up, and that is what is also called as a learning mechanism. So machine learning is all about developing algorithms where the central theme happens to be learning, and this learning happens on available set of examples, and these examples are just nothing but the data which is available with you in the context of that particular application. Now, for example, in the earlier case, the ice cream vendor has the data, which is the sales data, and then he has this data in the context of the temperature of measured on that specific day. And he has got this small data, and then using these two data, he wants to predict what exactly would be the sale on a specific day, having known the temperature on that particular day. Okay, so what is this machine learning all about, right? So machine learning, typically you have got multiple approaches where your computer programs have the ability to learn based out on the data it is actually handling. Right, the rules which are defined in the algorithm are not static rules. Now these rules keep on changing based out on the data my algorithm is looking at. Right, so I don't want to really do any explicit programming per se. I define using a specific strategy, and that particular strategy is called as a model technique. And using this particular strategy, I have my strategy work out on this vast collection of data elements, and accordingly I set up a bunch of rules, and these rules tend to become my model. Right, so machine learning is also identified as one pathway towards AI. Right, so let us understand a little more about machine learning. And here, this is a very standard slide. You just see the slides almost dumped everywhere. So I thought, why not? I should not do it also. This is a very simple picture which talks about three different areas. All of them are, subset of the other. So at an umbrella level, you have got AI, the artificial intelligence, where you typically talk about a whole variety of techniques implemented on a computer system that tend to mimic the human intelligence. Right? That is basically what AI is on a broad sense. And AI, very specifically, also includes machine learning. And what is machine learning? A subset of AI which identifies and includes a bunch of techniques that enable algorithms to perform some tasks, more specifically tasks like classification, tasks like prediction, tasks like estimation, etc. So these tasks can be performed from looking at data and enriching its performance. Let's say I come up with some performance P. I look at more data, my performance now would be P prime. P prime would be a better performance than P. And this is typically what we talk about fine-tuned, enhanced performance based out on the experiences. Right? So this is a machine learning where algorithms typically uh, tend to behave like smart, intelligent way of working out things. Machine learning also includes deep learning. And what is deep learning? It's a subset of machine learning where we are going to use one specific technology one specific set of algorithms called as neural networks, and these neural networks tend to work in a parallel manner, and then they try to mimic the overall behavior of the human brain. We will quickly talk about that. And primarily, these neural networks happens to be the core fundamental element of deep learning, right? And the deep learning algorithms typically use not just only one single neural network, but a multi-layer neural network, and it performs lot of tasks, not just only the learning, not just only the prediction, not just only the classification, but a whole bunch of other activities alongside as well. So deep learning are essentially very complex neural network implementations uh, to solve AI related problems, more specifically used in the context of images and audio and video related applications. So we'll talk a little bit of deep learning as well. So now deep learning is a subset of machine learning. Machine learning is a subset of AI. Sorry. So before we get on to the overall discussion, let me just quickly run through some terminologies. We'll be using this terminology quite often. So we'll start off with what we mean by feature. Feature is that specific trait of an observed data point. Now, for example, I have information that is recorded about, let's say, some patients. So the information which I record for every patient could be the patient's name, what exactly is the treatment he is seeking, what are the observed parameters and stuff like that. All those typically identify the trait of that particular person, the distinct trait of that particular person. So the trait is described by a set of features, right? So one of the feature could be, let's say, his height. Other feature could be his current BP level. Third feature probably could be his BMI index. These are all typically the features which describe that particular data point, that particular entity. Okay, so these are features. And what is a sample? Sample is typically nothing but a bunch of items which I select so as to use it for A, learning purposes, B, applying them, setting up a model, or whatever. So these are basically a bunch of data points that are taken. Might not be the entire set of data points, but a selected few bunch of data points over which my model can be prepared. Right? So a sample could be maybe a small extract out of a document, or a complete picture, or a part of a picture, a sound file, or a small snippet of a sound file, a video or a frame of a video, or could be a few selected rows in a database, or probably could be the entire table, and so on and so forth. So all these are typically the samples. And feature vector is an n-dimensional vector. Now, for example, I have a system wherein there is a camera, and the camera makes a picture of a particular subject. Let's say I'm the subject, and the camera takes a picture of the subject. And from here, my computer algorithm is supposed to be identifying who this particular person is. Right? So that is basically, let's say, the algorithm all about. So it will try to extract the so-called predominant features from my picture, tries to identify if these particular features typically mean the picture of Gokhale. If so, it will declare the fact that yes, I have recognized this photo or the picture to be of Gokhale, or else it can say no, I can't recognize this picture, stuff like that. So out over there, what are the features? The features of this particular thing could be typically what is the distance between the two eyes, what is the size of the nose, what is the ratio between the distance between the two eyeballs and the size of the nose, what is the size of the forehead, what is the angle of the cheekbones, and all of those parameters which you would like to identify critically the person in that particular photograph. All of them are recorded, and these become my feature elements, and all these are collected together. So I have a feature vector. Feature extraction is that particular process where you try to use techniques to extract the features from the data. And training and evolution set is essentially that particular part of the data which is used to train or build the model. And that is pretty very important. We'll talk about the significance of what is this concept of a training set. So here is yet another example. This is an engineering example. Here I talk about, let us say, a component testing. And here we have got a component, and this particular component is designed by a, let's say, a mechanical engineer, and then he comes up and then gives me a drawing. So there are typically some dimensions, and these are the 8 dimensions. He labels these dimensions as A, B, C, D, E, F, G, H, etc. And he says that these dimensions are the attributes, the defining attributes of this particular mechanical component. And he says that, okay, as part of testing, you need to measure all these dimensions and then tell me whether this particular component is good enough into production, or it has been accepted for production, or whether this particular component is rejected or the component needs some rework. So remember, now after the testing, he is now assigning a label to this particular component. Right, so every component that is getting manufactured, typically, let's say, by a CNC machine or by an operator, this inspection guy will do a component testing, and then he will attach a small label, right? So accordingly, he will just do what we call it as a classification. So if it is to be done this way, what the design people will say is, oh, okay, to make your life easier, don't really worry about all the 8 features. Pick up only the 2 features. These 2 features are the most prominent features, so I can call them as the principal features or the principal components. And these are the features H and D. Forget about the remaining features, only look at H and D, and then my parameter should be something like this. For acceptance, H and D should be within this range of 75 mm plus minus 1% and 50 mm plus minus 1%. And if the dimensions measured H and D are greater than 75.75 or greater than 50.5, then I have a scope to rework. Whereas if it is less than these values, then obviously it goes for reject. So these are some rules which are defined, and these particular rules can be set up into what is called as a rule base. So a rule base can be implemented by a very, very simple nested if type of a mechanism. Right, so pretty very simple. So this is what is called as a rule set, and that rule set defines a rule base, and that particular rule base will allow me to classify that particular instance of an object to be either accepted, rejected, or reworked. Right, so what I need to do, measure the dimensions and apply these rules for each and every sample and assign the outcome for each and every sample. So this activity is what is called as classification. Okay, now the question is, who provides this rule base? Obviously the design team in their specifications. Second thing is, these rules are static, right? So for example, there is one mechanic, and the mechanic says that, hey, if that particular dimension H is let's say 74.98, I know it still works, and he is telling this out of his experience. But as far as my rule base is concerned, this component would be rejected. So here now we talk in terms of bringing in a heuristic approach for classification, which means what? Is there a possibility for me to change these rules dynamically, looking at a whole set of data points which are available to me? So let us now talk about a different approach. This is what is called the model-based approach. Right? So assume that I've got an expert, and this particular expert critically measures these principal parameters, and we really do not know what type of rules he applies, but he decides directly the class. He does some measurements and then say, okay, this component is accepted, this component is rejected, this component is accepted, this component is reworked. So he just automatically apply his rules in his mind and then does the classification. That's very fine, and he is to be an expert, so because of which no questions asked. If he has taken one component, he says it is accepted, it is accepted. If it is rejected, it is rejected. Okay. Now the question is, how is this guy taking this decision? Is it possible for me to get into his mind to find out what exactly is the algorithm he is working out to decide this class? I need to know that. So what I do is silently, I take a notebook and then typically also make a noting. The noting says the fact that, okay, this is the dimension and the expert has said that this is rejected. These are the dimensions, the expert said that this is accepted. And I keep on doing that, I record this. And this becomes what is called as a scene data or a training data. So here it is height is this much, depth is this much, and outcome is rejected. Pardon me for the spelling mistake here. So this way, I've observed a few of these records from the training. What is this training data? This training data is the data which I have observed from an expert, and I would like to train myself to understand how the expert is actually working, how the expert is taking a decision, how the expert is classifying the component. So what I do is I use this data and then somehow get a wonderful idea and a clear picture about how the expert is taking decision. So I say that yes, I now have a clear model, a clear behavior of the expert's way of working. Having known that, then I say, okay, now I get this unseen data. That means what? New components come up and then I measure and then I get these two parameters. And from these two parameters, I now need to decide whether it is accept, reject, or rework. So what I do, I now use the model to identify the outcomes on new data or unseen data. So this is what I'm supposed to be deriving now. I'm using the model. So now the model based approach and the ML framework goes something like this. You have got the data which is available to you. This is called the training data. You use this data and then identify an appropriate algorithm. We call this as a learning algorithm. And using this learning algorithm, I create a model. So this is a model which has been learned, and the model having defined, model keeps on learning the moment it sees more and more and more of this particular data. So this operation is called as induction. So I've created a mature model and then I can store my model. So this way I can prepare different models, we have different techniques available. I can create different models. So I just have a pool of all these models. And when I need to really answer some query, so the query is, let's say I measure these values and then I now need to decide whether this particular item would be accepted, rejected, or reworked. I will do this deduction, and deduction is a technique wherein apply this test data on the model, and the model will deduce and then it will tell me what exactly is the outcome. So that is what is called as a model based approach. Typically, what we call an ML framework. So here is yet another small example. I given an image, identify the object. So here I now need to define something like this. Image of a gear. I have to define a function in such a manner that the function tells me the fact that yes, indeed, this image means a gear. This image means a bearing. This image means a bolt. Right? I need to do that. So what I need to do is something like this. Looking at this image, I need to extract some standing features out of this image and represent that as a small, let's say, a data set. So something like this. I look at the features, some properties. Do I see anything round? Do I see some elongated part? Do I see some teeth? Does it have spears? Does it have a chain? Does it have a groove? I see that, and then I can now also say that okay, this belongs to a category called as a gear. This belongs to a category called as bearing. This belongs to a category called as bolt. And I have now three samples, and these three samples have observed these features, and features are recorded into a feature set vector, and I just able to identify the core properties of a gear, core properties of a bearing, and core properties of a bolt. And mind you, these three records is highly inadequate for anyone to really get a complete understanding of what a gear really looks like. So if at all I use these three records, I probably, when I apply my model, it could probably look at this sort of a picture. It can find out that it has got teeth and there is also some bearings. So it could identify the fact that this could be a gear or a bearing. It is now confused. So the prediction is not crisp. The prediction outcomes are not clear. There is a fuzziness out there. So it now could be a probabilistic type of a prediction. So it can say, given this picture, I can possibly say that with a probability of 0.65, it is a gear. 0.35, it is not a gear. zero point 0.4, it is a bearing. 0.6, it is not a bearing. Right? So it can probably give me a probabilistic estimate of the predicted values. So here is yet another example. This could be predicted as a bearing or a gear. This also could be predicted as a bolt, simply because Hussein Bolt out there is very famous. He comes up in the news. So this could be also interpreted as bolt. So what we need to do is what? I need to somehow enhance this feature representation by looking at more and more data samples. This is pretty very important. So what is my machine learning? It's all about identifying a prediction function which operates on the features coming from whatever is the source. If it is an image, then it is the features coming out of an image. If it is a let's say a voice snippet, features coming out of that voice snippet, the frequency components of the voice snippet. If it is, let us say, a record from a database, so the specific parameters of interest to me, those particular column values, those particular attribute values now become the feature vector. So whatever it is, the feature vector would be operated upon, and it generates an output which is just nothing but a class, the output class. So most of the machine learning goes into distinct phases. The first phase is what we call as the training phase. We take the training data. Here it is a bunch of images. We call them as the training images. And for each and every image, we extract the image features, use that as part of a training. And for that, we also use what is called as a bunch of training labels and an appropriate training model algorithm, and ultimately come up with a learn model. So this learn model is has seen already images of maybe a few 100,000 images of such mechanical components, and it now has a very clear idea about what features make up a gear, what feature makes up a bolt, what feature makes up a bearing, apart from other things. And having learned so much, I can now use this particular model. So how do I use the model? This is now an image which I now need to identify. So my algorithm is subjected to this image, and my algorithm will now use this as a test image and extracts the features out of this image, and that particular features it applies on the model which has been prepared already, and the outcome of that would be the prediction, the predicted value. So please understand, there will always be two phases, two stages, the training stage and the testing stage. Training stage is where you see, work out on the available data to learn about the behavior of that particular aspect. Testing is where you actually handle the unseen data and then try to decide what this unseen data means. Right? If at all it is a prediction algorithm, you try to predict what is a class. If it is a regression algorithm, you try to predict whatever is the value from the given inputs, stuff like that. So this learning, you have got four different types. Very quickly, let me go through that. The first one is called the supervised learning. The supervised learning is a scenario where you have some expert, and this expert has seen already the data. A priori, he has assigned the correct class labels to each of the data point. And using this data, I go ahead to do the learning. When I say I am the machine learning algorithm. So that is a supervised learning. Unsupervised learning is a scenario wherein I just have the data, class labels are not at assigned, not known beforehand, and then it's something like the Ekalavya learning how to do archery. On a similar line, here you have got class labels not known beforehand, there is no supervisor, and the algorithm slowly starts building a model. It builds a model and then starts to apply the model to see if there are any errors. Based out on the errors, it will once again tweak the model, and slowly, in a few iterative approaches, few iterative cycles, it will learn, very much like the way algorithm is tutored by a teacher. So here there is no teacher, there is no supervisor, it's a unsupervised learning. Clustering is a classic example of unsupervised learning. and there could be semi-supervised learning, and semi-supervised learning is something like this. You have got unsupervised learning for few times, and then you validate whether the learning is correct by approaching a supervisor, and the supervisor makes some fine changes, and then once again you get into an unsupervised learning for some more time, and then once again periodically come back to the supervisor. So this is what is called as semi-supervised learning. And lastly, very important technique of learning is a reinforced learning, where it is all about goal driven learning. So you learn, and once you learn, you are awarded for the performance based out on the learning. And depending upon the award which you receive, you try to optimize, you try to earn more of these awards, right? So your objective is try to perform in such a manner by learning and learning and learning, so that your objective is to earn more of the rewards. So such a learning is typically what is called as a reinforced learning. So when you come down to the ML models, you've got a variety of them, right? You have got a variety of models. Uh, Primarily, you have these models as regression models, classification models, clustering models, outlier models, and some other models. So very quickly, I just mention a few of them here. Decision tree, random forest, KNN, neural networks, extension of neural networks is called as a convolutional neural network, CNNs, uh, very, very advanced forms of neural network implementations. CNNs is now pretty, very popular too. And these are all a variety of classification models, also naive Bayes and support vector machines. So these are typically the classification models. And the reason I'm listing out these models is you better watch out and then try to identify the fundamental way and approach built in into each of the model. All these models perform pattern recognition. All these models perform classification, but the way they do it is totally different. Number one. For your application, please understand this, for your application, it is very, very important to know what exactly is the model that you should be using, right? Let us say you have got random forest. Random forest may be not applicable in all cases. Neural networks might be good in some cases, might not be good in all cases, etc. So you need to identify which of these algorithms works fine for you. There is no silver bullet. There is no hard and fast thumb rule. So you need to try out each of this particular model to find out which model works best for you in that particular context of the data that is available. Okay. Clustering model. Clustering is a mechanism which is quite similar to classification. Given a bunch of data, you can segregate the data and then create, let us say, pools of data points, groups of data points, or clusters of data points. And this typically is an unsupervised learning mechanism. So it is called k-means and k-medians. These are the two approaches which are popular. Regression models are used for prediction. I already spoke about regression models, which is a chillax example. Then you have got outlier models, models which look at the data to find out whether this particular data is appropriately normal and nominal or not. There could be some data points which are extremely beyond a normal range, right? So these are what I call as outliers. Outliers are those data points which are not totally far away from a normal, let's say, a behavior of that particular system, right? Now, for example, a person like me uses a debit card, and then I perform ATM transactions. And if you look at my transaction history, my swipe values could be ranging from, let's say, 2,000 rupees to 10,000 rupees. So that is a variation of my swipes from my ATM machine. If there is suddenly a swipe of, let's say, a lakh of rupees, now this is a behavior which is not normal for Gokhale, right? So this is what is called as a behavior, a data point which is coming up, which is outside of the normal nominal behavior. So this has to be identified. This has to be triggered. This has to be handled. So for fraud detection and stuff like that, we typically use these outlier models. We also have got association rule basket market basket analysis models. We are going to talk about that a priori also a little later on. So quickly, let me just get on to a few more aspects about what this model is all about. When I define a model, I need to also identify how good the model is, right? So I need to have some metric for evaluating the performance of a model. So for example, expert is very good at classifying. So if at all I'm having my application, my computer algorithm to do a similar type of a job, my algorithm also has to produce a result which is on par with what the expert would typically be doing, right? There could be some predictions made by the algorithm which could be in error. Now, for example, a component which is supposed to be accepted has been wrongly classified as reworked, has been wrongly classified as rejected. Similarly, a component which is actually not right should have been rejected. My model says that this is acceptable. So both ways there is an error in the prediction. So I need to calculate and find out how many such errors are happening, and that gives me a parameter called as an error of my classification, and accordingly I can also identify whatever is the accuracy of my prediction. So to analyze that, we normally prepare a matrix representation. This is called as a confusion matrix. So the confusion matrix is something like this. Let us say I've got my actual class could be yes and no. I'm just taking a two-way classification. And the predicted class also could be yes and a no. And if the class is a yes and if it has also been predicted as yes, then the prediction is absolutely correct. If the class is no and it has been predicted as no, then also the prediction is absolutely correct. So out of all the samples, A number of times and D number of times my prediction is correct. C number of times and B number of times the prediction is wrong. So what is this A, B, C, D? So A is called as a true positive. Fact which is true also has been identified as positive. Similarly, false negative is B, right? It has been falsely classified. Similarly, false positive is C, right? It's a false has been wrongly classified as positive, false positive, and true negative. This is your D. And what does this basically mean? If I take these values and then I can now add up these diagonal elements A and D. So it is A plus D upon A, B, C, D, all these four values that typically tells me how many times my predictions are correct. So that is a parameter which is called as an accuracy, and that is one of the common metric that is used to evaluate the effectiveness of the model. People typically try to build models where the accuracy is a minimum of, let's say, 99, 99.5, 99.7, 99.9 percentage. 95 percentage accuracy is no good, especially in the case where these prediction results are being used for some very critical decision making activity. So that is also now what is called as the cost of an error, right? So if the cost of an error is very high, I have to ensure the fact that the accuracy which I demand from my classification or my prediction model has to be nothing less than 99.999, right? So let us quickly look at a few of these models. I spoke about regression, so let me very quickly tell you about that. So here is a typical scenario wherein I'm trying to set up a interrelationship between the temperature and the humidity. So I can define some sort of a linear relationship wherein I can say temperature is K times humidity value plus C. So what is this K? K is typically the so-called slope of a linear relationship. Okay, so prediction is one of the main focus of regression. So I use regression as a mechanism to predict the value of a given continuous variable based on another variable. So based on, let us say, temperature, I can identify whether I can play or not play. Based on, let us say, humidity, I can determine and estimate what will be the value of the temperature, stuff like that. So here you talk about prediction. In the first example, given a temperature, whether I'm going to play or not play, we call this regression as logical regression. Whereas given a humidity value, if at all I can estimate what would be the temperature, then you typically talk in terms of uh, a normal regression model, which could be linear regression or a non-linear regression. So here is a small example. I can fit all the data points and then define a straight line and identify a line equation, and that typically would be nothing but the model for all this data. Right? So I can now also use this model to identify what is the trend. So I can now say that this particular data points show a positively increasing trend. We call this as a northbound trend. Right? So I can also use this linear regression for trend analysis. Okay. There could be some other ways by which you can also do this fitment, right? You have a linear representation, or you could also go in for a higher order polynomial. Let's say order 4 polynomial, order 7 polynomial, order 21 polynomial. And as you increase the order, obviously the cost of prediction and the cost of estimation is higher, but you can just see the fact that the curves tend to be more smoother and thereby bringing down the overall error in your prediction. So you can also use this polynomials, higher order polynomials also for your prediction. So what are the applications of regression? Trend analysis, let's say temperature prediction or sales prediction or spend analysis. Spend analysis typically means, let's say, as I increase the advertisement budget and the advertisement spend, can I find out if the sales or the profits are also increasing? Can I set up a linear relationship between the two? So I can now have a regression model for my spend analysis. Okay, so people typically build these sort of models and to identify, okay, beyond some point, probably there is really no sense in adding more to my advertisement budget. Classification is yet another mechanism wherein we define a rule-based mechanism to partition the data into clearly defined class labels, clearly defined classes, and for each of these class, I assign a class label. Okay. So here is a small example of once again data that is available to me. I've got data put up into a Cartesian plane. This is about age and salary. Right, so I've got some people's representation out over here, and this typically means the fact that there is one person of a specific age and his salary is this much. So I guess these are basically the so-called scatter plot of these two parameters, and I have run a classification model, and then for each one of them I assigned a label. So red means what? Risky. Greens are all safe, right? Yellows are all high probable. And these black points are typically not considered in my model building simply because these points are way away from a normal distributions. So these are called as outliers. Okay. So I can now use this classification to assign a class label to these data points. Here I talk about data points which are defined over two parameters, two feature values, age and salary. Now the question is, now there is a new sample which is observed. So what should be the class for this? So classification is all about trying to determine the class of this new sample given the remaining other data points and their values and their associated classes. Okay, pretty very simple. By the look of it, I can just say the fact that this particular sample will be safe, will be green in color, simply because I see the sample pretty close to these two, right? So this is also a very simple visual way of trying to assess what will be the class label for this unknown new sample. Visually, I see the fact that this is pretty close to this point, so I can just say this is also going likely to be green in color. This is also called as a neighborhood information that is being used for estimating the class. So what are the classification models? There are plenty of them: decision tree, nearest neighbor, neural networks, and support vector machines. I'm not going to really go through all of them. Quickly, let me talk about this decision tree. A decision tree classification essentially is a mechanism wherein it takes a bunch of data items which are already worked on. This is already examined by an examiner. Each of the data point is already pre-assigned a class label. And using the so-called supervised learning approach, I build a flowchart like representation that allows me to navigate this flowchart or tree structure to determine the class of a new parameter. Okay, so the question is, how do I build this flowchart or how do I build this tree? Okay, so the first part is, from the data I build a tree, and if the tree happens to be not very clean and nice enough, I chop off some unwanted branches. I'm sorry, unwanted branches, that is called as pruning the tree. Having created a nice pruned tree, then I will use the tree, I will apply the tree, I will use the tree to classify unknown samples. So here is a small example. I've got this data, and this particular data is over 3 column attributes and 1 class. So I've got some refund, marital status, and taxable income, some parameters out over here. And from there, I will find out whether this particular individual is going to cheat, whether he is going to not pay the EMIs, or whether he is going to pay EMIs. So that is my class label. So what I do, I use this particular column values and then create a decision tree which looks something like this. Now the question is, how did I create that? That's a different story altogether. I have created this decision tree, and once I know this decision tree is come out from this particular data, based out on this particular data, I can now apply this decision tree on an unseen new data. So here is how I apply the model. So this is my decision tree, and now I have got the test data. Test data is, for this current sample, refund is no, marital status is married, his taxable income is 80K. Now I would like to estimate whether he would cheat or not, whether he would be paying my EMIs properly or not. So I'll just apply my decision tree starting at the topmost node, the root node. So I'll apply for my refund. Refund is no, so I traverse this particular path of the tree. Then I come down to marital status. I look at the marital status. Marital status happens to be married. So I apply that and then follow this particular limb of the tree, the branch of the tree. Then I look at this. These are the leaf nodes. Leaf nodes typically will have the class label, and I take this class label no and then determine the fact that this particular data, the value of cheat, the class will be equal to no. I have traversed this. So how did I come and deduce this? This deduction is based out on the tree that is built using this sample data. This was the sample data. So if the data was different, obviously now notice the fact that the tree that is generated would also be different, and probably the same result might yield cheat to be yes. So please remember the fact that the models will be different. If the model is different for the same test data, the outcomes might also be different. So how do I create this decision tree? Pretty very simple. Pick up all the data records, identify what is that attribute which can very clearly be used to create two subsets of the records in such a manner that one subset of the record contains values for the class label being the same. Okay, so which means what? Find out that particular attribute which can partition my input set of records in such a manner that each of the partition will contain a homogeneous set of class labels. If not, I will once again take this subset, recursively apply on yet another parameter, the second parameter, the third parameter, and so on and so forth. All right, so this is what is called as recursively applying a decision model at each and every value. So for that, what we do is we have got two approaches. I'm not getting into the mathematical details. One is what is called the Gini index based approach, other one is an entropy based approach. The Gini index based approach applies what is called as a probabilistic distribution function using some count mechanisms, and it will define, okay, how many counts I'm seeing for class equal to A or for class equal to B based on this particular attribute to be equal to true or false. Accordingly, it will try to partition the uh, data items, partition the input records. Okay, so that is how the Gini index works. Entropy typically works on a measurement of this uncertainty, and depending upon whether the overall entropy is increasing or decreasing, I will identify which of the attribute is acting as a better splitting attribute compared over to the other. Right. So you have got different techniques. I'm not getting into the details though. Using these techniques, you can build the decision tree algorithms. So you have got very popular decision tree algorithms called as a CART. This CART uses Gini index approach, or you have ID3, C4.5. It's called the classifier 4.5, and C5.0. All these three use entropy mechanisms to define the decision nodes. And what type of data can be used? You can use categorical data as well as continuous data also. So where are decision trees used? They are used for risk evaluation. Given a bunch of values, right? For example, there is a person, his age is 25, he's working in an MNC, right? He has already has a housing loan. Now the question is whether his loan application for a personal loan of 5 lakh rupees, should it be approved or not? What is the risk that is associated with granting this additional loan? Maybe my decision tree would tell the fact that yes, the person is having low risk, and if it is low risk, probably the bank will allow the loan to be processed favorably. So this is a simple example of risk evaluation. Similarly, I can talk about customer segmentation. Customer segmentation is a very popular technique that is used as a machine learning application, wherein, let's say, for a given type of a product or a product category, I can identify what type of a segment this particular product is going to cater to. If at all I can identify that, I can now target this particular segment of customers to sell a specific type of a product. So this will obviously give me a direct access to a more potent set of buyers rather than offering my product to every Tom, Dick and Harry. Right? So this is what is called as customer segmentation or customer profiling, as we call it. Right? We can profile my customers based on the typical types of purchase patterns which I've observed. I can find out whether this particular customer has the potential to buy an iPhone 15 or not. Stuff like that. So you have got basically a lot of applications of decision trees wherever you would like to do, let us say, a prediction, a class prediction more specifically, then you are going to use decision trees. There is another small extension to decision trees called as random forest. Yes, sir.